Welcome! Today, we're looking at a technology that could totally revolutionize artificial intelligence. We're talking about a new engine for AI, one that doesn't run on digital code, but instead uses the fundamental physics of waves to power the huge models we interact with every single day. Because, here's the dirty little secret. We all see the amazing things large language models can do, right? But behind the curtain, there's this enormous and frankly growing problem of just how much power and raw computational muscle they need. It's a massive energy drain that could seriously limit where AI goes next. So let's really frame this problem. These large language models are, without a doubt, incredible. But they are absolutely ravenous for computation. They're built on a type of math that, when you scale it up to billions and billions of parameters, creates this massive computational traffic jam. And just look at how ridiculously lopsided their workload is. A staggering 90 to 95% of all the thinking an LLM does when it's generating a response for you, it's all just one single type of math. Everything else we think of as complex AI logic, that's all crammed into that tiny 5% slice. It means our super advanced chips are spending almost all their time and energy on just one brutally repetitive task. And that one task is matrix multiplication. At its heart, it's really just a gigantic series of multiply and add operations, over and over again. It's the basic way AI finds patterns and connects ideas. But when you have to do it billions of times on a traditional chip, well, that's what causes the traffic jam. So how in the world do you solve a problem like that? Well, some researchers have come up with a really radical idea. What if we just stop? Stop using digital switches, the ones and zeros, and instead let the laws of physics do the math for us. This is a complete paradigm shift, moving from digital logic to pure analog waves. And the difference is just fundamental. On one hand, you've got traditional digital computing. It's built on billions of tiny on or off switches. It plods along, step by step, and all that switching back and forth burns a ton of power. But on the other hand, you have this analog approach. It uses the physical properties of a wave, like its height and its timing, to represent numbers. And the magic here? It does all the math at once, in a single, continuous flow. This quote from the research really just nails it. Instead of a computer painstakingly calculating every single multiplication and addition one by one, the computation just happens as a wave passes through a specially designed device. All the operations happen at the same time, in parallel, at a speed that's basically limited by the speed of light itself. Okay, so you're probably wondering, how on earth does this actually work? It's pretty fascinating. The device is what's called a programmable wave-based analog metastructure. And the core of it is an architecture they call a direct complex matrix, or DCM. Let's just follow a signal on its journey, okay? First, an input wave, which is carrying a number, enters the chip. Right away, a power splitter makes a bunch of identical copies of that wave. Each one of those copies then gets sent to a little programmable multiplier that tunes the wave's height and timing. That's the multiplication part. Then, a combiner gathers up all of these newly tuned waves and just adds them together. The final wave that comes out the other side is the answer to the entire matrix problem. It all happens in one smooth physical process. So here's the critical connection. We have this amazing piece of hardware that computes with physics. But why is it so perfect for what large language models do? How does this get us out of that traffic jam we talked about? Well, this table lays it out perfectly. The vast majority of what an LLM does is just different flavors of that same matrix multiplication. Stuff like projecting your input into queries' keys and values to figure out context, or calculating attention scores to see which words matter most. All that heavy, repetitive lifting is a perfect job for the analog hardware. It's only a few specialized nonlinear tasks, like softmax, which helps the model make a final choice, that are still better suited for a good old-fashioned digital chip. So the advantages here are just huge. You're talking about computation that happens in nanoseconds. You get true, honest-to-goodness parallelism where everything gets calculated at once. It's insanely energy efficient because you're not constantly flipping billions of transistors on and off.
And critically, the whole thing is reconfigurable, so you can program it with new information on the fly.
Now, I know what you're thinking. This sounds incredible, maybe a little too incredible, almost like science fiction. But good engineering isn't just about cool ideas. It's about facing the real-world problems head-on. And yeah, this approach has some big engineering hurdles to overcome.
And what's so great is that for every major challenge, there are already clever solutions being worked on. The AI matrices are too big for one chip? No problem. You use a technique called tiling, breaking the big problem into smaller, bite-sized chunks. Worried about noise or precision in the analog signal? The fix is a mixed precision design with constant on-the-fly calibration. Worried it's too slow to reprogram? You solve that by batching operations together and caching the most common data. See, these aren't just dreams, they're solvable engineering puzzles.
So all of this leads to the most likely vision for the future. It's not about analog computers completely replacing our digital ones. No way. It's about building a powerful hybrid system that really uses the best of both worlds. You can almost picture it like a new kind of data assembly line. A process kicks off on a digital chip, then it zips over to the analog metastructure for all the heavy lifting, the projections, the attention scores. Then it might pop back to the digital chip for a quick specialized task like softmax, before going right back to the analog chip for another round of matrix math. It's all about using the right tool for the right job at every single step. So where are we going to see this first? Well, the most likely role is as an accelerator, a coprocessor that sits right next to a GPU and just takes all that boring matrix math off its plate. It's absolutely ideal for inference. That's running a model more so than training one from scratch. And the smartest way to start is probably with medium-sized models, to prove out the tech before scaling up to the absolute giants.
And this really leaves us with a final, kind of mind-bending thought. For decades, we've pushed computing forward by making our digital switches smaller, faster, better. But maybe, just maybe, the next great leap for AI won't come from writing better code, but from harnessing the fundamental laws of physics to compute at the speed of light.